I am indeed Frank DiTraglia, and I'm an econometrician, which is basically a fancy name for a social science statistician who works in an economics department. And my research is a bit of a mix. Some of it is theoretical and some of it is more applied. But broadly speaking, I'm very interested in developing methods for trying to untangle cause and effect. Now, today, I'm not going to be telling you quite so much about my own work specifically. What I'd like to do instead is to try to give you some of the background that underlies that work in the form of a kind of a crash course on causal inference. Will earning a PPE degree from Oxford increase your lifetime earnings? Does eating bacon sandwiches cause cancer? Does watching Fox News make you vote Republican? And will owning a dog increase your lifespan? So each of these questions concerns the causal effect of some treatment, and we usually use the letter D to represent a treatment, on some outcome Y. Now, the word treatment sounds a bit like a medical trial, but in social science, we tend to use the word more broadly. So a treatment could refer to any kind of factor whose causal effect that we hope to learn. So viewed from this perspective, the treatment could be earning a PPE degree at Oxford. The treatment could be eating bacon sandwiches. It could even be watching Fox News or owning a dog. I'm not completely certain, but I'm relatively confident that no one has ever carried out an experiment that compelled people at random to study certain subjects at certain universities, or to watch Fox News for 16 hours a day, or to own a dog. However, papers have indeed been written and published that use data to try to estimate exactly these causal effects. Data sets in which the treatment does not arise from a random experiment, but is instead naturally occurring, are called observational data sets. And because many of the most interesting and important treatments in social science really can't be randomly assigned in an experiment, social science statisticians have developed a set of tools for trying to study treatment effects when all that's available is observational data. And today, what I'd like to do is introduce you to the key ideas behind some of these tools, and show you how researchers have used them to try to shed some light on an age-old question, namely, how much is a university education worth? So here's Alice, and Alice earned a PPE degree at Oxford. It's not very widely known, but it's true. So now she earns £75,000 a year. Suppose that she had instead gone to Oxford Brookes. Would she still have earned as much? The fundamental problem of causal inference is that we can never observe a person's counterfactual outcome. In other words, we can never know what her outcome would have been if her treatment had been different. Fundamentally, this idea of a counterfactual is a within-person comparison. So in effect, I'm asking you to imagine two parallel universes. There's one universe where Alice attends Oxford, and there's another where she attends Brookes. So the causal question of interest, when you think about it this way, is basically how much does the Alice in our world earn compared to the other Alice who is through the looking glass? Now, this is a thought experiment. We can never actually have two Alices or two universes. So if we want to learn about treatment effects in the real world, what we need is some kind of combination of methods and assumptions that will allow us to substitute this idealized within-person thought experiment with some kind of an actual practical between-person comparison that we can really make in real life. And that is effectively the challenge of trying to do causal inference with observational data. So what's the first idea? Well, perhaps we could get a large group of people who graduated from Brookes, and we could compare their wages to those of another large group of students who graduated from Oxford. Here's a table that does just that. So as you can see here, the median salary for Oxford graduates, which I'm pointing to with my mouse pointer, is quite a lot higher than that of Brookes graduates. So the difference is around £15,000. Okay, so does that tell us that the causal effect of attending Oxford rather than Brookes is £15,000 per year. Well, probably not. And the reason is that this is really an unfair comparison. It's not comparing like to like. It's not comparing apples to apples. Oxford and Brookes, first of all, don't offer the same degrees, and their students differ in many ways other than just which university they attend. So a particularly important difference is that the universities have very different entrance requirements. So here's a particular example, and for this example, I tried to find 2 degree programs that are relatively similar, one at Oxford and one at Brookes. So at Oxford, we have the E&M degree, Economics and Management, and Oxford requires that applicants have grades of A star, A, and A at A level to gain admission for E&M. Brookes, on the other hand, has a similar degree in economics, finance, and international business, but Brookes actually only requires grades of B, C, and C for applicants to that program. So the applicants are not the same, and the students are not the same. A useful way of trying to summarize some of these differences in entrance requirements and student characteristics across universities is by examining the distribution of UCAS tariff points among students. This is fun for me because I didn't know what UCAS was or what a tariff point was until last year. So I feel especially excited now that I get to talk about them as though I know. So UCAS is the University and Colleges Admission Service, which you probably know better than I do. And UCAS tariff points, quote, translate your qualifications and grades into a numerical value, end quote. So roughly speaking, we can view these tariff points as some kind of a measure of academic preparation and ability. Higher numbers are better. So I looked this up, and a student who earned grades of an A star and an A at A level would gain 152 UCAS tariff points from this, whereas a student who earned grades of B, C, and C would only gain 104 points for that result. The distribution of UCAS tariff points varies substantially both within and between university. What I mean by that is, at a given university, students have different numbers of tariff points on the one hand, but then if you compare across universities, students also have different numbers of tariff points comparing, say, Oxford to UCL. We can see exactly how this breaks down by looking at the following figure taken from a recent report put out by the Institute for Fiscal Studies. I'm going to discuss that report in some more detail shortly. So each of the bell curves in this graph shows the distribution of UCAS tariff points among students at a particular university. So this dark blue curve right here, helpfully, is Oxford. And this green curve over here that's toward the middle of the chart, that's Loughborough. Brookes, alas, is not on the chart, so I'm going to have to use Loughborough as my stand-in for Brookes. Okay, so how do we read one of these curves? Well, the way that it works is we choose a range of values on the horizontal axis. So let's suppose we choose the range of values from around 400 to 600. If we look at the area under the blue curve, the one that represents Oxford, what we see is that most of that area is between 400 and 600. What that tells us is that a majority of Oxford students have between 400 and 600 tariff points. If we look at the same range, 400 to 600, but we instead look at the area under the green curve, that's Loughborough, we see that the area is less than half. And what this tells us is that a minority of Loughborough students has between 400 and 600 tariff points. Now, we don't want to make too much of this because there's actually a fair degree of overlap between the green and dark blue curves. And what that tells us is that there are definitely some Loughborough students who have more tariff points than some Oxford students. But on the whole, if we wanted to talk about UCAS tariff points on average, Oxford's curve is shifted to the right relative to Loughborough's. So if we want to take these UCAS tariff points as some kind of a rough and ready measure of academic preparation and ability, this would suggest that Oxford students on average come to university with higher levels of these variables. So Oxford students do earn more when they graduate, but they also enter university with higher levels of preparation and ability. What that means is that it's perfectly possible that attending Oxford has literally no causal effect on your wage, but earning high grades at A-level does. It's possible, I'm not saying it's likely, but it would be consistent with the data. So in statistical parlance, we would say that ability and academic preparation confound the relationship between attending a particular university and your wage. A confounder is defined to be anything that affects both the treatment and the outcome. In this case, ability is a confounder because it affects both which university you attend and your wage. So we can think of many other possible confounders in this example, not just ability. What kind of school did you attend, family income, demographics? There's many possible confounders. The key point is that in the presence of confounding, merely comparing the outcomes of people who are treated against those who are untreated does not reveal a genuine causal effect. Confounding could make it look like a treatment doesn't cause an outcome, when actually it does. It could also make it look like it does cause an outcome, when in fact it doesn't. Confounding could even reverse the direction of a relationship. It could make it look like a treatment that's really beneficial is actually harmful. So confounding is a huge problem. Now, when we carry out an experiment, we don't actually have to worry about confounding. And the reason is that in a randomized controlled trial, we randomly assign the treatment D. What that does is it breaks any relationship between other factors that determine your wage and the treatment. So for example, if we were to randomly assign students to different universities without any reference to their characteristics at all, just by flipping a coin, then what we would find, among other things, is that the UCAS tariff points would on average be identical at Oxford and Brookes. Indeed, any characteristic of the students would be equal on average between Oxford and Brookes, and we know this because of the way we would design the experiment. Of course, we haven't done such an experiment, and we're not going to. We just don't have access to experimental data for answering this question about university attendance and wage. So for the remainder of this talk, I'm going to show you 3 approaches to trying to solve the problem of confounding when we only have observational rather than experimental data. And along with these 3 approaches, I'm going to show you an example of each from a real paper where practitioners use this method to try to get a handle on something related to the returns to education. The first approach goes by a number of names, but probably the simplest is to call it matching. What matching does is to compare treated and untreated people with the same values of any confounders. So for example, we might compare Oxford students with a certain number of A-levels, A stars at A-level to Brookes students with the same A-level results. The idea is to repeat this comparison for every possible combination of values for the confounders. Whenever you make these comparisons, you're comparing like with like. So the comparisons aren't subject to the objection that I raised on the previous slide. By combining the estimates you get for all these different subgroups, matching gives us a way to estimate the overall causal effect of, say, attending Oxford compared to some other university. Matching is very simple, it's very intuitive, and it's quite powerful. But in order for it to work, we do require some assumptions. The first of these, crucially, is that all of the important confounders are observed. So if family income, for example, confounded the relationship between university attendance and earnings, we would need to be able to observe family income to fix the problem with matching. If we did not, in fact, observe family income, then matching can't help us to resolve that particular confounding problem. The second requirement that we need is called overlap. What this means is that for any value of the confounders, we need to have some people who are treated and some people who are not. So earlier I suggested that UCAS tariff points are an important confounder when you're trying to learn the causal effect of attending Oxford. If we were going to do matching, then what we might do is to say compare Oxford students with 600 UCAS points to Loughborough students with the same number of points. Now, in order for this to be possible, the bell-shaped curves I showed you a few slides back have to overlap. And here I literally do mean physically overlap. In other words, there need to be some students at Loughborough who actually have 600 UCAS tariff points. Otherwise, we can't make the comparison. There's actually a little bit of tension between these two requirements. The more confounders that we try to adjust for, the harder it is typically going to be to satisfy this overlap requirement. There are many statistical techniques that I won't go into today that can partially help us to get around this issue and improve the quality of the matches that we form. But one thing I just want to be completely upfront about is that implementing them in practice does require judgment. It also requires subject-specific expertise. So these tools are quite powerful, but they are not a free lunch. Okay, so with that caveat, I'll now show you the first real example. This is an example that uses matching to try to determine the causal effect of attending different universities and studying different subjects at university. It's drawn from this recent report from the Institute of Fiscal Studies that was carried out in collaboration with the Department of Education. This figure is drawn from the paper, and what it shows is the relative difference in wages for UK women across different university degrees. Now, there's a lot going on in this figure, so I'm going to spend a moment explaining it. The red dots in the figure are raw comparisons, and the black dots use a matching approach to try to correct for confounding. So let's take a look at the far right of the figure. So here we have people who studied medicine. So if we take a look at the red dot, what this tells us is that women who studied medicine, on average, earn about 75% more than women who studied other subjects at university. After we adjust for the differences between medics and other graduates besides which subject they studied, however, the figure falls to around 30%. What this means is that medics earn, on average, only about 30% more than similar individuals who studied a different subject. So again, what is the idea here? We want to find two groups of people who are as similar as possible, women from the same background, with the same A-level results, etc. One group of the women studied medicine and the other didn't. That's the comparison that we're making here using matching. And when we make that comparison, we find a very different result. Medicine still looks like it commands a wage premium, but nowhere near as large a wage premium. If we take a look towards the center of this figure, we take a look at computing graduates, the situation is actually reversed, which is quite interesting. So these women earn slightly less than average if we just look at their raw salaries compared to other women. But once we take into account that they also differ in their characteristics from the average woman, we find that, in fact, computing graduates earn 10% more than comparable women who studied different subjects. Now, the authors of this report freely acknowledge that it's quite unlikely they've really controlled for all the possible confounders. So to a certain extent, we have to take these results with a pinch of salt. However, these results suggest that comparing raw wages dramatically overstates the true effect of studying a particular subject at university. And the way we can see this is that the black dots in the figure are systematically closer to zero than the red dots. In other words, adjusting for confounding dramatically reduces the difference in wages. This figure is similar, but rather than comparing university subjects, it compares universities. So again, we're looking at relative differences in wages for UK women, but here we're comparing across different universities. So every dot in this figure is a university. The colored dots give raw comparisons, while the black dots use a matching approach to adjust for confounding. And the colors, yellow, red, blue, and green, indicate which group the university belongs to. So for example, the yellow dots are Russell Group universities, which are considered to be more prestigious. So let's take a look at the dot all the way to the right. I hope you can see where I'm pointing with my mouse. This dot is LSE. So what we see is that women who graduate from LSE earn over 70% more than the average female graduate. However, take a look at the black dot, which adjusts for confounding. After we do this, we find that LSE female graduates only earn about 35% more than similar women who attended different universities. The other yellow dots around here in the figure are Oxford, Cambridge, UCL, and we see a very similar story applying there. Again, it's very likely that the authors haven't managed to observe all the relevant confounders. Nevertheless, these results do suggest that comparing raw wages dramatically overstates the true causal effect of studying at an elite university. Again, these black dots are systematically closer to zero than the colored dots, and the effect is particularly large for the most prestigious institutions. Now, for matching methods to be effective, we need to observe all the important confounders. And in some settings, this may be a reasonable assumption, while in others, it clearly isn't. So for the rest of the talk, what I would like to show you is two strategies that empirical social scientists turn to when one or more important confounders just can't be observed. The first of these is called regression discontinuity. And the easiest way to explain it is by using an example. My example comes from a recently published paper that studies the effect of attending an elite public institution in India. Quite unlike the situation in the US, the most prestigious colleges in India are in fact public. So given the choice, effectively everyone would prefer to attend a public rather than a private institution. Admissions to public colleges are based on a threshold rule. So anyone whose senior secondary school exam score exceeds an appropriate threshold is admitted, and anyone whose score falls below this threshold is rejected. These thresholds vary from year to year, they vary from subject to subject, but crucially, the applicants do not know the threshold, and all the applications are evaluated anonymously, so evaluated blind. The situation is depicted in the diagram at left. If your senior secondary school exam score, X, exceeds the threshold, T, then you attend a public college. So we say that you're treated, D equals 1. If X does not exceed this threshold, D equals 0. So now you're attending a less prestigious private college. In the parlance of regression discontinuity studies, we call this special variable X that totally determines whether or not a person is treated the running variable. So the running variable is a rule that completely determines who's treated and who's not. And here's the crucial insight. People with exam scores just below the admissions threshold are effectively identical to people with exam scores just above that threshold. Let me put this another way. Suppose you take an exam and you score 59.9%. Is that really meaningfully different from scoring 60%? I can assure you, having marked many exams in my lifetime, that it's not. It would be very easy for a small difference like that to be purely random noise in the marking. It could be purely random noise in how well you felt when you arrived at the exam. You might have gotten lucky or unlucky, and one of the questions you know really well was on the exam. So tiny differences in test scores are just luck. However, if you move from just below the threshold for admission to a public college to just above, your treatment will jump discontinuously from 0 to 1. So for people who are near the threshold, it's as if the treatment had been randomly assigned, even though we know it wasn't really a random rule, it was a fixed administrative rule. This is the key idea behind regression discontinuity. And we can use it to estimate the effect of attending an elite public institution on later life outcomes. This figure is taken from the paper I cited on the previous slide. And as in my diagram from above, the horizontal axis in the plot shows the running variable, which is this secondary school exam score. and the dashed vertical line indicates the admissions threshold. Unlike the previous diagram, here the vertical axis doesn't represent the treatment, it represents the outcome. So this is average salary 10 years after graduation. The green dots in this plot are averages rather than individuals, and here's how they're constructed. So you put people into bins based on their secondary school exam scores. So you find the people with their scores in a particular range, put them in a bin, and then you calculate the average score in that bin. The line is the line of best fit for these green points. In other words, it's the regression line. Similarly, on the right-hand side of the threshold, we have some average values of salary for people whose scores fall into different bins, and we have a line that best explains the relationship between those two. Now, the lines themselves don't actually matter, but what does matter is the distance between them on either side of the threshold. So this distance right here. Recall that everyone below the admissions threshold attends a private college, while everyone above attends a public one. What we see from the figure is that people whose exam scores are just very slightly below the threshold actually earn dramatically lower salaries later in life than those whose test scores are just slightly above the threshold. So if this means anything to you, the difference actually amounts to around 0.7 standard deviations. But because falling just below or just above the threshold is effectively random, we can conclude that attending a public college causes people to earn quite a lot more later in life. So attending an elite Indian public institution does appear to cause you to earn more, but does it cause you to learn more? An interesting feature of the Indian higher education system is that public and private college students take standardized exit tests in their chosen subjects upon graduation. This figure is identical to the previous one with a single change. Here, the vertical axis plots average exit test scores rather than average salary. As before, the key thing to look for is the distance between the two lines on either side of the admissions threshold. If we see a big jump, then that means that there's a causal effect of attending a public college. Now, if you squint really, really hard at this figure, you can just about make out a tiny, tiny gap between the lines. But you can take my word for it, this gap is far too small to be of any statistical or practical importance. So what this tells us is that attending a public college has zero causal effect on how much people actually learn during their university years. And taken together, these results may seem a bit puzzling. So if private college graduates earn just as much as public college graduates, why are employers paying them so much less? It's very hard to say for sure. I don't have a great answer for you. Presumably, public college graduates have access to more valuable peer networks that might help them later in life. Also, prestigious firms may be more likely to recruit at elite institutions. I remember when I used to teach at Penn, I discovered that there were some companies that literally would not recruit outside of the Ivy League, which is very strange given that there are many elite US institutions that are in fact public, places like UC Berkeley, but there were some recruiters that simply wouldn't consider graduates from Berkeley. So that may also have something to do with it in the Indian context, although I'm certainly much less familiar with it. But whatever the reason, it is a somewhat dispiriting result, particularly for those of us who teach undergrads at a well-regarded university. When applicable, regression discontinuity methods provide an extremely powerful tool for causal inference that does not really rely on strong assumptions. There is, however, a slight caveat that I've glossed over, and that concerns the nature of the causal effects that this kind of approach will allow us to uncover. If you think about it for a minute, there's no reason that we should assume the causal effect of attending an elite public institution is the same for everyone. Maybe people from a less wealthy background benefit more than people from a wealthier background. What regression discontinuity is really telling us is the treatment effect for the kind of person whose score in high school exams is close to the threshold. Strictly speaking, this doesn't actually tell us anything about the effects for other groups of people in the population. So we learn a causal effect with minimal assumptions, but we are kind of learning it for a special group of people. We might say that the results are internally valid, but they might not be externally valid. They might not apply to other people. To try to say more about what this result means, you need to some extent, extrapolate it beyond what you're actually learning from the study. So as I've said, regression discontinuity is extremely powerful, but it's not always applicable. The key to the regression discontinuity design is that there is a variable called the running variable that completely determines who's treated and who's not. But in many interesting examples, it's impossible to find such a variable. Fortunately, there's a related approach that's much more broadly applicable, and it's called the method of instrumental variables. Quite a lot of my research involves instrumental variables, different kinds of problems that they present, and different ways that we can try to use them to answer interesting questions. An instrumental variable, or an instrument for short, is something that affects the treatment D, but is unaffected by any confounders U. Traditionally, economists like to use the notation Z to refer to a variable that satisfies these requirements. And it's worth just distinguishing this a bit from the regression discontinuity setting. So here, Z does not have to completely determine the treatment. So an instrument does not have to completely determine the value of D. It just needs to affect it to some degree. For instance, rainfall has been used as an instrumental variable for voter turnout. Now, rain doesn't force you to stay home on election day, but it does tend to reduce turnout on average. So this is very different from the regression discontinuity example we just saw, where nobody below the threshold can attend a public institution. Since Z and D are both observed, we can easily check this first requirement for an instrumental variable. In other words, we can easily check that rainfall is related to voter turnout. But the second requirement is quite a lot harder. The reason that we need an instrument in the first place is that we're worried that there might be some important confounders that we can't observe. If we observed all the confounders, then we could just do matching. There'd be no point for the second part of my talk. But if there are some important confounders that we can't observe, then there's no way to check if they're actually related to the instrument. So applying the method of instrumental variables requires us to construct an argument for why it's reasonable to assume that a proposed instrument is valid. And that's a technical term that we use to mean unaffected by confounders U. The method of instrumental variables has an extremely long and venerable history in applied economics. I remember when I was doing my master's degree in statistics, we had an interesting textbook that had a chapter called econometrics. This is funny because, of course, econometrics, would fill many volumes of a book, not just one chapter. But that book effectively equated instrumental variables with statistics and economics. So there's a very strong relationship between economics and using this technique of instrumental variables. And indeed, for the past few decades, there's been something of a cottage industry of trying to come up with very clever instruments. As I sometimes like to joke to my students, if you can think of a clever instrument that no one has used before, you're pretty much halfway to tenure. So to illustrate this method of instrumental variables, I'm going to take you back to one of the most famous papers that ever used the approach. This is a 1991 article by Josh Angrist and Alan Kruger studying the impact of compulsory school attendance laws on earnings later in life. I checked this morning, and I think this paper has nearly 4,000 citations on Google Scholar. So it's been extremely influential. The paper begins with a striking and surprising observation. In the US, at least, people born in the first quarter of the year tend to complete fewer years of education on average. So this figure plots average years of education by quarter of birth for US men between 1930 and 1940, using data from the 1980 US Census. The digits that are printed below each point indicate quarter of birth. So all the way at the extreme left here where my mouse pointer is, that number 1 refers to the first quarter of the year 1930. All the way over here at the right, that number 4 refers to the fourth quarter of 1940, and so on. If we take a close look at this plot, we will discover that in every year except for 1940, men born in the first quarter ended up attaining fewer years of education on average than those who were born in quarters 2 through 4. If you look at the scale on the vertical axis, you'll see that the differences aren't particularly large. So you might be wondering, well, is this effect real? Or maybe it's just the result of random noise. You may also notice that there are no error bars in this plot, and there's actually a reason for that. So when pollsters report, as they did earlier this week, for example, that say 70% of Republicans do not believe that the 2020 election was, quote, free and fair, they don't just report the 70% number, they add a margin of error. So in that particular example, it was plus or minus 2%. What a margin of error does is reflects the likely magnitude of any random differences that could emerge between a sample of around 2,000 voters who were contacted in a poll and the population of millions of voters. Importantly, the figure on the slide is not based on a sample. It's calculated from census data, so it actually includes all US men born between 1930 and 1940. So there's no difference between the men in this plot and the population as a whole, because this is the population. And that's why there's no margin of error, in case you're wondering. Okay, so resolving that small issue, why is it that men who are born in the first quarter complete fewer years of education? Well, according to Angrist and Kruger, quote, children born in different months of the year start school at different ages, while compulsory schooling laws generally require students to remain in school until their 16th or 17th birthday. In effect, the interaction of school entry requirements and compulsory schooling laws compels students born in certain months to attend school longer than students born in other months. So what Angrist and Kruger do is to use quarter of birth as an instrumental variable to try to unravel the causal effect of schooling on wage. Truth in advertising, this is not to do with university, this is to do with high school. So I snuck this one in, but it's still about the effect of education on later life outcomes. We saw from the previous plot that indeed this instrument, quarter of birth, is related to the treatment, years of education. So it satisfies that first requirement for an instrumental variable that we talked about a moment ago. Now, what about the second requirement, the requirement that the instrument be valid? For this to be the case, quarter of birth would need to be unaffected by any unobserved confounders. Angrist and Kruger argue that this is indeed a reasonable assumption. They say, quote, because one's birthday is unlikely to be correlated with personal attributes other than age at school entry. So to unpack this statement a little bit, there are many, many, many unobserved factors that could influence how many years of education a person obtains and her later life outcomes. Things like demographics, family background, etc. So what Angrist and Kruger are arguing here is that these other unobserved factors are unrelated to when specifically within a given year you're born. Assuming that Angrist and Kruger are correct, and indeed quarter of birth is a valid instrument, we can use it to estimate the causal effect of an extra year of education on wages in the following way. First, we calculate the average difference of wages between men born in the first quarter and men born in quarters 2 through 4. That's the numerator in this fraction here. Men born in the first quarter actually earn less on average later in life, it turns out. So this difference in the numerator is negative. Next, we calculate the average difference in years of education again, between men born in the first quarter and men born in quarters 2 through 4. On average, men born in quarter 1 have fewer years of education, so this difference in the denominator is also negative. To find out how much of the observed difference in wages can be attributed to differences in education, the method of instrumental variables takes the ratio of the two quantities. You may be wondering why that's a valid thing to do. It takes a fair bit of math to establish, but it turns out that indeed, if the assumptions are warranted, that's how you can estimate the causal effect. So since both of these differences are negative, the ratio is positive, and it's equal to 0.1 with a margin of error of 0.05. It turns out that in this example, for reasons I won't get into, wage is being measured on the log scale. So to interpret this result, we have found that an extra year of secondary education increases a person's wage, annual wage, by between 5 and 15%, which is quite a substantial effect. And if you're being very, 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 very careful, you may have wondered, wait a minute, what's the margin of error doing in here? I thought he told us this is census data. And indeed, we do have census data on education and quarter of birth, but Angrist and Kruger only have wage data for a subset, for a sample of men. So there is a standard error associated with the numerator because just like in a poll, we're not actually observing the wage for all the men, even though we are observing the education and the quarter of birth for all the men. Okay, so the crucial question here really is, do we believe that quarter of birth is a valid instrument? Is it really true, or is it really reasonable to assume that a person's birthday is uncorrelated with personal attributes other than age at school entry? Well, I promised to discuss 3 papers in this talk, but now it's time for a special surprise bonus 4th paper. About 7 years ago, Buckles and Hungerman revisited this quarter of birth instrument. They looked at a US data set that includes information on both birth dates and family background, in particular, characteristics of a child's mother. In the years since 1991, which is when Angrist and Kruger published their original paper, there have been many, many studies using season of birth as an instrumental variable, more than 20, in fact. And across these studies, researchers have found that US children born in quarter 1, or more generally in the winter months, earn less, pursue less education, and actually have lower measured intelligence on average compared to those born in other parts of the year. Intriguingly, researchers in other fields have found a correlation between season of birth and schizophrenia, autism, dyslexia, extreme shyness, and even suicide risk. So what on earth is going on here? This is extremely strange. Well, Buckles and Hungerman propose a simple explanation, namely that children born in different seasons, quote, are not initially similar, but rather are conceived by different groups of women. So what exactly does that mean? Well, here's one of the figures from their paper. It's very similar in design to the one from Angrist and Kruger that I showed you before, but rather than showing the characteristics of the child, this plot concerns the characteristics of their mothers. So what do we see? Mothers who give birth in the winter months, such as January, are disproportionately likely to be teenagers compared to mothers who give birth at other points of the year. Notice that January is on the top of each of these little seasonal wiggles throughout the entire period from 1989 to 2001, and a similar pattern emerges when using data from different decades. This seasonal pattern is actually very substantial. Teen births are around 10% lower in May than in January. And to give you a little bit of context about that, you may be aware that there was a much lauded decline in teen births during the 1990s. Well, that decline over the entire decade was approximately as large as the seasonal variation in births to teen mothers from January to May. So this is quite a substantial effect. Women who give birth earlier in the year are not only younger on average, They're also less likely to be educated. So in this graph, we can see that the percentage with a high school diploma peaks in May, and the percentage without peaks in January. They're also less likely to be married. So Buckles and Hungerman conclude from this that, quote, the well-known relationship between season of birth and later outcomes is largely driven by differences in fertility patterns across socioeconomic groups, and not merely natural phenomena or schooling laws that intervene after conception. The fact that family background characteristics have strong relations with both season of birth and later outcomes indicates that season of birth will likely fail the exclusion restriction in most instrumental variables settings. That means season of birth is an invalid instrument. And indeed, if you try to correct for this fact, you will find that the estimated returns to education from Angrist and Kruger falls pretty dramatically. It falls by something between about 25 and 40%. So where exactly does this leave us? If there's one thing that I want you to take from this talk, it's this. Causal inference is extremely hard, and it always relies on assumptions. Social scientists have a powerful toolbox for studying treatment effects in settings where a randomized experiment is impossible or impractical or maybe even unethical. But like any tools, the methods of matching, regression, discontinuity, and instrumental variables depend crucially for their success on the skill with which they're actually used by practitioners. So I don't want to sound negative. We can and we indeed do learn about cause and effect from observational data, and that's quite extraordinary. But doing so requires knowledge of the problem we're studying. It requires a willingness to question our assumptions by looking at other data, and it definitely requires a good amount of old-fashioned intellectual humility. So if you like this talk, perhaps you'd like to learn more. Why not audit my class on treatment effects? I'm actually about to give a 2-week mini course on treatment effects to the MPhil students in the economics department. My teaching materials are already online. These are the ones from last year. They're available at my website. Just go to DiTraglia.com and click on teaching. I'm going to be updating these materials over the next few weeks. I'm also going to add some video mini lectures, and these will kind of pick up where the talk I've given you today leaves off, digging a bit more into the mathematical details of how we actually do this and why it works. There are many, many books on causal inference and treatment effects that you might find interesting if you enjoyed this talk. If you're just starting out, my favorite one is called Mastering Metrics. It's by Angrist and Pischke. It's slightly silly in places and a little bit opinionated, but it does an extremely good job of introducing the subject to beginners, and it contains many examples beyond the ones that I showed you today, and some other methods for causal inference based on observational data. The same authors also wrote a more advanced follow-on book that's aimed more at master's students. That's called Mostly Harmless Econometrics, and I would call that my recommended second port of call. And if you come across an interesting causal inference question in your job or your life more broadly, if you have some interesting data and you're wondering how to start thinking about it, feel free to send me an email. I may not know the answer, but I'll try to point you in the direction of some information that could help.